Welcome to this introductory offering of the course Mathematics of Waves. This is the very first lecture, and my objective is to give you an idea of the approach we'll be using and what we want to cover. And there's a series of like 10 lectures in all, and the lengths are like between 15 to and 30 minutes long. This first lecture may be a little longer because I'll try to give you an overall view of what we are going to do in this course. Anyway, so let's get started. So, as you know, waves are very much a part of our everyday life, and I've just shown here two examples of that, two very different examples. One is acoustic waves, which has been with us a very long time. Anytime we talk, we generate these acoustic waves which go across the room to someone else and they hear us. Right. Now, the other example is relatively new in the sense that, say, 200 years ago, they were unknown. But today, it's very much a part of our everyday life in the sense that every time you send a message on your phone, what happens is the message gets converted to an electrical signal. There's electrons that jiggle around, which generates an electromagnetic wave, which goes to the other side of the world and is received there, where again electrons start jiggling and somebody can read your message. And so this is something we are using routinely all the time nowadays. And these are two very different kinds of waves. In fact, their velocities are very different. Acoustic wave is many orders of magnitude slower than electromagnetic waves. But when you describe them mathematically, they can be described by much the same equations that look much the same. There is a parameter here, this velocity. And of course, this function f, what it represents, is very different for an acoustic wave compared to an electromagnetic wave. In the case of acoustic wave, which is like pressure waves, there's molecules that are displaced. So that's what this f represents. Whereas an electromagnetic wave is a more abstract thing in the sense that this quantity is an electric field or a magnetic field. Now, in either case, there's also a source term, something that generates the wave. So for acoustic waves, it's my vocal cords that are vibrating and generating the wave. Or it could be a guitar string that you pluck, for example. And with electromagnetic waves, as I've just mentioned, the source is some kind of an oscillating current, when electrons are jiggling around. So again, very different physical things, but the mathematical description looks similar, this basic wave equation. And in general, I guess in all of science and engineering, a common thing that we try to learn is how to extract the physics from the math. That is, you describe things in terms of these abstract symbols, the math. But what you're describing is very much this physical world, things that we can touch and feel, right? And how to connect them is kind of what all our training is about, how to learn how to connect the math to the physical world. And in this course, we have selected a very particular class of physical phenomena, namely waves. But this idea of connecting physics to math is a much more general thing. Now, usually the way you do it is, we have some textbook problems, simple problems, which you can solve using analytical methods. And that's what you do in textbooks. So using the analytical properties of certain functions, you try to write down solutions. But of course, the real problems of the real world, they are usually not that simple. They do not permit these analytical methods. And that's when you go to numerical methods. You formulate it in a way that a computer can solve it. But those are mainly for professionals usually. So when you take an introductory course, you only learn these analytical methods. Now, in this course, what we propose to do is kind of reverse this. So we start with these textbook problems, but we start by using numerical methods to solve them and look at the solutions. So we look at the solutions to the equation using these very powerful codes that are now available. So you see there in Python or MATLAB, there are very powerful functions that are available with which you can directly solve the equation and get and compute the outcomes and compare it to the physical phenomena. So we'll kind of start there, use these very powerful things to extract the physical phenomena, but then we want to use the analytical methods to understand what we are getting, because even though the computer can solve it, that's not enough. We need to understand it in order to be creative with it and to do, and to design interesting things, useful things with it. Now, other point I want to mention then is I said that this is the equation you'll see in textbooks usually describing waves of all kinds. But the equation we will be using in this course looks something like this. See, it's the variable of interest forms a column vector x. And the size of the column vector changes. We'll explain how and why. And then there's a matrix which multiplies this column vector. So it's like dx dt equals ax plus s. That's the form of the equation that we'll be dealing with. And this often might look to you very different from the standard wave equation, but at some point we'll show you that the two are really equivalent. You could go from one to the other. It is just that this thing with the one-time derivative is much more convenient in terms of solving, because basically you see what solution of this equation involves is it tells you what is dx dt. So if I give you x at one point in time, you know how it changes. And so you can calculate x at the next instant in time and the next instant. And that's how you can get your entire solution. So you could do that yourself, but of course, that time step needs to be adjusted carefully, in order to make sure that you're getting accurate results. And these are things that you can bypass if you just use these functions that are available on MATLAB and Python. So you just write one line. You define your functions, the a and the s, and call this function, and it will solve it for you. That's it. So just a couple of lines and I've solved it. And it doesn't matter what the size of this matrix is, what the size of the column vector is. The equations look basically the same. So it's relatively easy to do this, right? Which is why it's convenient to use this first and get a solution, and then go ahead and try to understand it. So let's start with the simplest case where n is equal to 1. And so basically it's dx dt equals ax plus s. And all these are just numbers, not column vectors or matrices. Well, is that physically relevant? Does it describe anything useful? Well, let me just give you two examples. Like a parachute falling due to gravity. You can write the rate of change of momentum is equal to the force acting on this. And the force has two parts, one due to the gravity and the other due to the air drag or the friction, which is proportional to the momentum. The faster you go, the more the frictional drag. And so you have this term. So you can see that has exactly the form, this generic form here. Another example, which may be more familiar if you're from electrical engineering, and even if not, these are simple circuits, you probably have seen this. If you had a resistor in series with a capacitor and you apply a voltage source and you look for the voltage across the capacitor, you'll get an equation that looks, again, much like our generic equation. Well, what do the solutions to this equation look like? Well, as I said, you could just use MATLAB or Python to get it numerically. That's what I've done here. So if you had a source term that was 0 before time t equals 0 and then suddenly stepped up, what the solution would do is, this response would be is, it would grow exponentially towards some final value. And this is exactly what you see physically also, like a parachute kind of starts with 0 momentum and then builds up to some final momentum. And the charge on a capacitor does the same. Now, in order to understand these solutions, though, one tool that's very useful is, instead of a step response, to look at what's called an impulse response. So imagine that you're hitting it not with a step function, but with a impulse, something that is 0 generally, but for one short interval of time, it has a high value. And the area under this curve is 1. So if it is non-zero for a length of time dt, then the amplitude is 1 over dt. Now, if you do that, again, that too, you can numerically look at the solution, and what you'll find is the solution looks like an exponential. So if a is negative, it just dies out like a decaying exponential. A is positive, it grows. If a is 0, stays constant. So that's the impulse response. And this usually gives you some insight into the nature of this system. And once you know the impulse response, you could find the response to other types of sources as well. Now, that solution had no oscillations. But remember, this course is about oscillators and waves. So what kind of a equation would give me oscillatory solutions? Well, one example that we'll look at is something like this, where n is equal to 2. So I've got two components. See, and this matrix that's coupling them has this form. You have some quantity omega here on the off diagonal, but it's negative and here and positive here. And this equation, when you solve, and you could do it numerically, you will actually get oscillatory solutions. If you hit it with an impulse, either S1 could be an impulse function or S2 could be an impulse function, and you'll get something like this. So that just comes out numerically. But then the question is, how do I understand it? Well, that's where this approach is usually very useful. And that is this idea of diagonalizing that matrix. So there is a basis transformation that you can perform so that x1, x2, s1, s2 are now transformed into this x1 tilde, x2 tilde, s1 tilde, and s2 tilde. And we'll, in the actual course, when we talk about this, we'll talk about the details. But of course, the real advantage of doing this is that this matrix, which was off diagonal, is now converted into a diagonal matrix. And the elements on the diagonal are the eigenvalues of that matrix, which actually happens to be minus j omega and plus j omega. J stands for square root of minus 1. Now, what's the advantage of that? Well, because it's diagonal, it means x1 and x2 are not coupled to each other. This is essentially two separate equations. And each one kind of looks like what we started with, namely a one component simple thing, for which we had seen that the solution was e to the power at. Now the solution will be e to the power j omega t, plus j omega or minus j omega. And as you know, exponential of j omega t has a real part and an imaginary part, and there's the cosine and the sine, which are oscillatory functions. So that's why that equation gives you an oscillatory response. Physical relevance. Does this describe anything physical that we're interested in? Well, one example is, instead of an RC circuit, consider an LC circuit. And what we'll show in the actual lectures is, indeed, if you write down the equations for this circuit, you can put it in this form that looks exactly like that, like our generic form. But one thing I should mention is that in order to get it in this form, where these terms have exactly the same magnitude. You notice I have an omega here and an omega there. In order to do that, I actually had to scale the current with a variable z0, with this quantity z0, you see. And I chose the z0 in such a way that these two become equal, you see. If you didn't, then what would happen is it would still be one will be negative, one's positive, but these wouldn't be equal. It would be something else. Of course, the eigenvalues would still be the same. The eigenvalue, if you check it out, actually depends on the product. But it is convenient to write it in a form where these two are equal. Okay. And that makes it look just like our generic equation. Now, I think it's in the third lecture that I show that there's a whole variety of physical systems, very different physical systems, all of which are described by much the equations that look much the same. This LC circuit I just talked about. There's a mass and spring system, which would also give you similar equations. You can think of something going around in a circular orbit, like a stone tied by a string and you twirl it around. Or it could be a little magnet whose magnetization is subject to a magnetic field. All of these, at the end of the day, will be described by an equation that looks something like this. And this matrix will have eigenvalues plus j omega and minus j omega. Okay. Now, when you look at actual systems, though, there's a little more that you need to add to it. Namely, you see, previously I only had an L and a C with a voltage source driving it. In general, you could have a current source driving it. But more importantly, you'll have resistors associated with this inductor and the capacitor. And when you include those, the diagonal terms won't be zero, but you'll get some negative quantity here. See that? You see, previously we had zeros on the diagonal, but when you include this, you'll get this negative quantity. How does that affect things? Well, if you look at the impulse response, you'll now see a decaying decaying oscillation, right? And so this you'll get if you just simulate it numerically. How can you understand it? Well, again, look at the eigenvalues. If you take a matrix like this, the eigenvalues will have this form. Actually, this imaginary part could be a little different from this omega that I had written here. So probably I should have put an omega prime here in general. But apart from that little thing, point is that the eigenvalues there'll be two of them. There'll be complex conjugates of each other. And previously it was minus j omega and plus j omega. Now they have a real part that is negative. And so instead of e to the power at, you now have e to the power minus alpha t, e to the power j omega t, which then gives you decaying oscillations. If you look at the real part or the imaginary part, you have these decaying oscillations like you see. So these eigenvalues are a very good way to get some insight into what it looks like. Now, one last thing, and then we can move on to waves. That is, see, it is a 2-week course. Now, the first week we talk about oscillators, and the last item that we pick up is this idea that if instead of a delta function source, we have a sinusoidal source. So supposing this source term is cosine omega t. Then the question is, what is the response of the system? And what you'll find when you do this is that gradually the response will build up. If you are on resonance, in the sense, if your driving frequency is the same as the natural frequency of the circuit. Kind of like pushing a swing. If you want it to build up, then you push at just the right times. So if you then look at the amplitude that you finally get after things have settled down, as a function of your applied frequency, you'd usually get this sharp response like this. That when your external source has the same frequency as your natural resonance frequency, you get a big response. And when you're away from it, you don't get much of a response. And the peak of this curve is inversely proportional to this alpha. So if the alpha is 0.01, the peak is like 100. You see? But then the width of this curve is directly proportional to alpha. So if I made alpha equals to 0.1, what would happen is instead of 100, it would be only 10, but then it would also get broader. And what you can show is that the area under this curve is 1. And so you can write the power that is delivered by the source. If you ask this question, how much power does the oscillator absorb from your source? You'll get an expression looking something like this. There's something that depends on the strength of the source, the square of that, and then Z0, that was the scaling variable I'd mentioned before, this omega, and then there's a delta function right at the resonance. Right? Delta function, which basically means something whose width and height are kind of inversely proportional, and the area under the curve is 1. This I'll come back to a little later again after I've talked about waves. Now, the second week of lectures is about waves. See, we kind of set the basics about oscillators that we need. Now, for waves, the basic idea is if you take a bunch of oscillators and string them in series like this, so that one feeds into the other, next to the other, and so on. So you have, say, capital N sections, then the solutions to these will look like waves. How do you describe it? Well, same equation as before, but previously we had a 2 by 2 equations, a voltage and a current. Now I got N voltages, voltage in each of these sections, and I got N currents, current in each of these sections. So this entire column vector is now 2n by 1. And this matrix we are talking about is 2n by 2n. So that's fine, but as far as our numerical code is concerned, you could use exactly the same function, MATLAB or in Python, and you can look at the solution. So I'm giving you an example here where you had 100 sections. So it runs from 1 to 100 on this side. And what I'm plotting here is the voltage on each of those sections as a function of time. So this axis is voltage, this axis is time, and the color tells you the amplitude. See? So most of it you can see is blue, which means it's very, very small. It's like 0. But this little ray is basically tells you what the impulse response is like. You hit it, so at this end, so at first you have a big signal here, and then as time goes on, it propagates towards the other end. You see? And that's what this picture is showing. Now, what if I were to drive it with a sinusoidal source? That means cosine omega t type of source. Well, then you see, if I look here, you'll see pluses and minuses, because a sinusoidal source at that point will be oscillating between a plus value and a minus value. And this whole thing will be propagating down. So all these streaks propagate down to the other end. So that would be what a sinusoidal response would look like. Now, what kind of physical systems could this describe? Well, as I said, each one is like an oscillator, like an LC circuit. So circuit-wise, it's like as if you have strung together L's and C's. And this is sometimes called a ladder circuit. It would be a good way to describe a coaxial cable, where you have two conductors. There's an inner conductor and an outer conductor. And you can break it up into little sections, and each section, this is kind of the inductance per unit length, that's the capacitance per unit length. So to get an accurate description of your coaxial cable, you kind of have to go to the limit when the length of each section becomes very small, tends to 0. But the basic picture is the same. It's a string of oscillators. Another totally different physical system that could be described the same way, and we'll describe this, is a transverse acoustic wave on a guitar. In a guitar, you have these strings that are tied between two fixed points, and you pluck them and they vibrate. And it will be described by almost exactly the same equations. You see, actually, the fact that you see the two ends are fixed, they cannot vibrate, that is equivalent to putting a short circuit in the electrical case, where the voltage is zero. But the point I'm trying to make is very different things. This is a transmission line, electrical signals. This is an acoustic wave, but very similar equations. And once you understand the behavior, once you know how the equations behave, you can use it for different types of physical systems. Now, we then go on to waves in 3 dimensions. You see, like the example I'd given before, the acoustic wave. When I talk, the waves are usually spreading out in 3 dimensions. Electromagnetic waves, they spread out in 3 dimensions. And the thing is, that too you can visualize as if it's a string of oscillators in all directions, as if you have kind of taken these little blocks, each block being an oscillator, and connected them out in all 3 directions, forming a kind of a cube. See? And of course, for the acoustic wave, as you know, you need a medium. That is, if you talk in a vacuum, then nobody will be able to hear you. The medium is very important. So you can kind of see where these oscillators come from because of the molecules vibrating. But in the case of electromagnetic wave, I guess it's more surprising because it actually propagates through vacuum. So the point is, even vacuum is kind of composed of these little LC circuits going out in all directions. Now, if you want to describe it numerically, well, same story as before. It's just that now, if there are small n number of sections in one direction, then overall you have like n cubed units, which means these matrices kind of get big. You see, when I do the one-dimensional problem, let's say I had 100 sections in series. Okay, but then in 3 dimensions, it'll be 100 cubed, like a million. So the problem gets extremely big. See? But you could solve it numerically if you wanted. It's just that it gets harder with increasing dimensionality. But the one very important concept I want to convey in this course is this idea of normal modes. You see, earlier I had mentioned how in order to extract understanding, it helps to take this A matrix and diagonalize it. And at that time, we just had a 2 by 2 and we diagonalized it to get insight. Well, even when it's 2n by 2n, you can still diagonalize it, you see. And the point is, at the end, you'll get n independent oscillators. And that is very useful, this concept. These n independent oscillators, which are called the normal modes. And because you see, after all, it is a whole lot harder to solve one problem of size 2n by 2n than it is to solve n separate problems, each of size 2 by 2. Actually, even to do a 2 by 2, as I mentioned, we reduced it to 2 1 by 1 problems, if you remember. So this idea is a very powerful one that's widely used. See? And one example I'll give you is, like, supposing we want to know what a simple antenna will do. I mean, how much power will it radiate? So this is a little oscillating current element, something called the Hertzian dipole. Right? And it radiates out electromagnetic waves. I'd like to know how much power it radiates. Well, I know how much power is delivered to a single oscillator. That's what we did in the first week. Earlier I mentioned this. That's what we do in the first week. Well, all I have to do is take that expression and now sum over all these independent modes. And when you're in free space, those modes can be labeled with what I've written here as k, this k vector. And what we'll show you is you can actually perform this sum analytically, and we'll do that to get an expression for what's called the radiation resistance. That is, you see the power that's radiated, after you go through this, you'll find it's proportional to I0 square. And this quantity here is often identified as the radiation resistance, as if the power was getting dissipated in that resistor. And that will show is you'll get this. This is a standard answer. If you look at any textbook, talk about antennas, you'd see this would be one of the first results you'd see there. So this is not a particularly important antenna. I mean, this is kind of a textbook description start. See, and if you took a course in antennas, you'd learn about all kinds of more complicated antennas. But here I'm just using the example to show you the power of this normal mode approach, that as long as you understand oscillators, one oscillator, you can view this complicated thing, this electromagnetic waves radiating out in space, as just a power that's delivered to lots of independent oscillators. And you could sum it up to get the correct answers. So now I think you can roughly see what this course is about. Hopefully you're getting a feeling for that you see, kind of start, I spend week one discussing different types of oscillators, you see, and getting these results for oscillators where capital N is equal to 1. You see, it's a 2 by 2 matrix. So you start with a 1 by 1 and then 2 by 2. And then in the second week, we talk about how you go from oscillators to waves, this concept of normal modes, and how you can discuss these 1D waves and 3D waves. So that's what we'll be discussing. And before we get started then, let me just mention one other thing. And that is that I'd mentioned that this equation here, everything we do, we'll try to kind of use an equation of this form as your starting point. And in order to solve it, as I mentioned, you can use Python or MATLAB to extract the physics from the math. But if you wanted to solve it yourself, then what you do is you turn this ddt operator you break up this time axis into little steps of delta t, and write that equation in this form, where given x at a time t, you multiply it by a matrix W to get x at time t plus delta t. So that source term becomes this b that you add to it, and this ax becomes this wx. See? Now, of course, if you're doing it yourself, then the big question is what delta t to use, because if you use too big a delta t, then it won't correspond to the original situation, because these two are equivalent only when delta t tends to 0. But if you really make delta t very small, then to simulate a certain length of time will just take you forever. So there are optimal delta t's that you have to use if you are doing it yourself. Of course, the nice thing about using this MATLAB or Python is those codes do it all for you. You don't even have to worry about it. You just give it the A and the S and they'll do it for you. But when you look at it pictorially like this, you might notice a similarity with how neural networks work, in case you're familiar with that. Neural networks are widely used in modern machine learning and artificial intelligence. And there also you have a set of nodes, and there's a synapse which kind of multiplies the signals at those nodes with a matrix and generates another output. But in the case of neural networks, a very important element there is a nonlinear element that's involved. Because you see, without a nonlinear element, you have this principle of superposition. Namely, if A is a solution, B is a solution, then A plus B is also a solution. And that is the basis for this idea of normal modes that I mentioned, which I said is very powerful in terms of understanding and prediction, is this concept of normal modes. So as long as you don't have a nonlinear element, usually there are no surprises. The response is for any system. I mean, as long as it's linear, it's relatively easy to understand how it will behave in terms of this normal modes. But once you have nonlinear elements, the possibilities are much richer. So you could view that as a challenge in terms of analysis or as an opportunity. In fact, I'd say a lot of the power of neural networks comes from because there's an nonlinear element. That's why it can do things that you may not, that are hard to foresee. See? But any neural network, though, also has a linear part to it. That's the synapse. And this is an operation that has to be carried out many, many times over. And so one of the big challenges at this time is how to do this part fast and efficiently. And of course, the usual way of doing this part is with a digital computer. Like I mentioned, with MATLAB or C++, you write a code to do this, but that uses a lot of energy and is not very efficient. What would be nice is if you could design a physical system whose natural physics does this for you. So in that sense, although this course is about how to extract the physics from the math, one use for it would be is to use the physics to do the math for you. Right? Something people call physical computing, right? So anyway, so that's an aside. Just wanted to mention this connection to neural networks that you may find interesting. But broadly though, I hope I have been able to give you an idea as to what this course is about and what we are trying to do, what I'm trying to convey, and the approach that we'll be using. And what I'd really appreciate from you is your feedback, because this is just an introductory 2-week offering, and we eventually want to develop a 5-week version, and then even go beyond, take up other topics. But what I'd like to know is, in this course, do you find it useful? Is it clear? What things could be elaborated on? What other topics would you like to see? Would you like to see more on classical waves? Maybe a little more depth, maybe more different types of waves? Would you like us to talk about Schrodinger waves? The Schrodinger equation that's described as these probability amplitudes? Or would you like to hear more about quantized waves? You see, this equation, you could use it to describe electromagnetic waves, but classical electromagnetic waves, but it won't have the photon aspect to it. The photons, as you know, what it says is that these electric fields and magnetic fields are kind of quantized. You could have 1 photon, 2 photon, etc. And that is not quite contained in an equation like this. You need to take another step to get these quantized waves. So we could cover that as well. So anyway, so what I'd like is your feedback on what you'd like to see. Firstly, do you like what you see? And would like to see more? And if you like to see more, then what is it that you'd really like to see? Well, it's time to now get on with the course. So coming up next, we'll start with this simplest differential equation in the next lecture. Thank you.